Okay, this next short video, well, the other one wasn't as short as I thought initially, but I think it was clear enough, maybe. If you have questions anyway, just let me know. This second one is about energy in simple harmonic motion. Now, in the document that I sent you, they talk about energy in simple harmonic motion in what I would say a very superficial way, right? I guess they just don't want to give you all the answers, but I think it's important that we go a little bit deeper. So the graphs that you got there were this. So you have a graph of energy versus displacement. You know that displacement can go between negative A and positive A for the motion, and then the kinetic energy, for example, will be something like this, as we saw there, because the object has zero kinetic energy, so this will be kinetic energy. But then the gravitational potential energy will behave in the elastic potential energy if I'm talking about a mass spring system, right? So forgot to say that, but we're talking about a mass spring system. So obviously in the extremes of the oscillation about the equilibrium position, negative A and A, the kinetic energy will be zero because at those points it stops. But then the elastic potential energy in those points will be maximum because that's when we have the maximum stretching or compression of the spring. And right at the center, the elastic potential energy will be zero. So you get something like this, right? Now, if you add them together, you get the graph that they were showing there of total energy. So let me say this is potential energy, and then the total energy of the system is always the same, right? And we were saying how if an object has 10 joules of total energy, then at all points the kinetic and the potential will be 10. Maybe the kinetic is 5 and the potential is 5, or 2 and 8, or 7 and 3, but it will always, if you add them, it will always add up to that total value of 10 in that particular example. Okay, now this is like the first approximation to the topic, but then what about the object? What about the variation of energy with the object? So let's think of, again, a mass spring system. So we're going to talk about this system, this mass. Oops, let me just, it was a little bit too long. Okay, let me just erase it like this. So this will be your spring, and this will be your mass here, and that mass will be moving between two extreme positions about the equilibrium, negative A and positive A. And let's say that at time 0, the position of the object was at its maximum, and the initial velocity of the object was 0. That means that I just took this object and I pulled it to the right, and when I was there it had 0 velocity, and I just released it and the oscillation got started, right? And it started moving back and forth. Now what I wanted to see is this. Let me make this a little bit shorter. So if we graph displacement versus time for this object, we realize that because it started at a positive position, right, with 0 velocity, the graph is going to look like this, right? So I'm going to identify some points. So let's say this is point A. That's where the oscillation started. This is point B, the first time it goes through the equilibrium position. Then this is point C, when it gets to the maximum displacement to the left. Then this is point D here, the point where it comes back to the equilibrium position, but it's moving in the opposite direction. So I'm going to say this B was going to the left and this D is going to the right. And then point E up here is this one, right? So A, it started moving in that direction, but then point E is when it got back there, right? And then it repeats over and over and over and over, right? So this will be again B, this will be C, this will be D, this will be E, and so on, right? So how is energy changing there? That's a very important graph because it's gonna look similar, but it has, oh, sorry, where's my page? Okay, here. It will look similar, but it has actually a kind of tricky difference that I need you to be aware of. So let me say, okay, we're here. Let's see how energy, let's say kinetic energy versus, oops, that's a terrible horizontal axis. So, yep. Okay, stay there. There you go. That's a little bit better. So let's look at energy and identify some points. So at the beginning, at point A, what was the velocity? You're right, I'm assuming the velocity was 0 because it started with 0 velocity and it started moving. Then when it got to point B, it was moving the fastest, right? You need to realize that between point A and point B in the diagram, in the figure here, when it's moving in this direction from A to B, it's accelerating all the time because the spring is pulling. And when it gets to point B, it actually has its maximum value of kinetic energy. Is moving the fastest, right? What happens when it gets to point C? What will be the value of the kinetic energy? Think about it. If you need to pause, pause. You're right, the value of the kinetic energy is going to be 0 at point C because that's where it stops, right? And then what will happen when it's back at the center of the equilibrium position, but moving in the opposite direction, that it's for point D. So for point D, it will have again the maximum velocity, meaning that it has maximum kinetic energy, but it's in the opposite direction. Now, if you think about it, kinetic energy is equal to 1/2 mv squared, but this can never be negative. It doesn't matter if the velocity is negative or positive. 1/2 mv squared, because you're squaring the velocity, this will always have a positive value. So it's unlike the displacement versus time graph, the kinetic energy versus time graph cannot go negative. And I forgot to put my time axis here. So that means that the energy will be maximum at point D. Now, when it goes back to point A, it will be back to 0, right? Because that's when the object stops. So in one cycle of this, look at what happens to the energy. It increases to a maximum, then decreases to a minimum, increases to a maximum, and then decreases to a minimum. And if I keep graphing that, it's going to have the same behavior, right? That graph looks terrible, but you get the idea. And it will be just repeating over and over and over. Now, let's take a look at times. When did this whole thing complete a period, right? It completed a period at point when it's back at point A, or if you want, oops, what's happening? Wait, oh, that's right. So when it's back at point actually E, well, E and point A, they're kind of the same thing. So if I were to label the times here, this is time 0. Point E is 1 period, right? Point C is the second time it reached zero velocity, and that happens when it's on the other extreme of the oscillation. So this is t over 2, this will be t over 4 when it reaches the maximum, and then 3t over 4 when it reaches the other maximum. Now if you compare that to the graph of displacement versus time, we know that this will be t, right? And this will be t over 2, and so on. So in one period, this completes this full cycle of displacement, right? Now, look at what happens in one period of energy, right? In one period of energy, it goes from 0 to a maximum back to 0. So you would say that it has completed one full cycle, but actually that takes you only until t over 2. So you still have half the oscillation to complete. So in one oscillation of displacement, that is in one whole period, the energy kind of cycles twice, right? And the reason is that the energy is always a positive quantity. So what happens in the first half of the period will be repeated after the second half of the period. So this is a very usual thing to be used in paper 1 questions. Well, sometimes in paper 2, they can give you a graph of energy versus time that is going to look something like this. And they ask you what the period is. Most students would say that the period is from here to here, because that's when they see one oscillation of energy was completed. But what they don't realize is that actually this first half, or this first cycle of energy, is completed only in half a period. So the full period is actually this one. This should be the period of the oscillation. Now, the other thing that I wanted to make you aware of is what happens with gravitational potential energy, right? So let's say that this energy here is, I'm not going to say that it's kinetic, I'm going to say it's just energy. So I'm going to say the red one will be kinetic. So you get this, right? So that's your kinetic energy, the one in red. And then in green, I'm going to draw my potential energy. The potential energy is going to have the same behavior, but opposite. You need to remember that when the kinetic is minimum, the potential is maximum. When the kinetic is maximum, the potential is minimum, and so on. So when one of them is maximum, the other one will be 0, and the other way around. So if you graph that is going to look something like, okay, let me see if I can do that. Yeah, so it's going to look something like this. Right? Always having the exact opposite behavior. And at any point, if you take a look at the two graphs and you add their value, what you're going to see is that they add up to exactly the same amount, because the total energy, I knew that was going to happen, because the total energy has to be conserved, right? Because in simple harmonic motion, we don't allow for energy to be lost. So this would be your total energy here, and the the green one will be the potential energy, right? So just keep this in mind. These graphs are important to have in your notes, and thank you for watching. Bye bye.